Lesson 1-6, transformations of functions. A family of functions include graphs and equations of graphs that have at least one characteristic in common. So the equations of each of the functions are going to look very similar, such as if I had f of x equaling x, this would be similar, or part of the same family if I did f of x equaling x minus 4 plus 5. They would all be in the same group, but one's transformed. They'll look slightly different, just move either up, down, right, or left. The parent function is transformed to create other members in a family of graphs. So this one right here is a transformed of the parent function f of x equaling x. Some parent functions that we'll be looking at, a constant function is just a function where f of x equaling a, where a is any number. So this would be like a horizontal line or a vertical line. Here, the domain for this horizontal line is all real numbers, and the range is the same number where it crosses the y-axis. So a would always be the same number here. An identity function is also a linear function, but this one is where f of x equals x. So whatever x is, y is. It is the parent function for most linear functions. The domain and range will always be the same, all real numbers. Then we have absolute value functions. The parent function of absolute value function is f of x equaling the absolute value of x. And the domain is all real numbers. And the range is greater than or equal to 0. And then we have quadratic functions. Quadratic functions are those functions where they have a quadratic in it. So f of x equaling x squared. The domain is all real numbers, and the range is f of x, or you can think of it as y, is greater than or equal to 0. Now, when they refer to translations is one of the kind of transformation you could have on a parent function. So translation is a transformation in which a figure is slid from one position to another without being turned. So rotation is another transformation. Translation is like a slide. You're sliding from one point, either sliding to the right, left, up, or down. How do you determine if it's supposed to go up, down, right, or left? It all is based on the equation f of x equals x minus h plus k. So the h, whatever h is, so again, h, whatever h is, that goes to the right or to the left. So if h is positive, the graph is moved to the right. When h is negative, so this really should be a plus h. When h is negative, the graph is translated to the left that many units. This k, whatever's out here, if it says a plus k, then that goes up. And if it says a minus k, when k is less than 0, that would go down that many units. Let's take a look at our first example. It says graph g of x, the transformation of f of x equaling x squared, translated down 4 units and left 3 units. What this is saying is g of x will be translated 2 units to the left. That means this is x plus 2 squared, and then 4 units down, which would be minus 4. So if I were to graph this one, I would have a point at -2 down to -4. And then everything else would be the same. So if I put a -1 in for x, -1 plus 2 is 1. 1 squared is 1 minus 4 is -3. I have a point here, and I can mirror that one, and I would have a point there. I have enough to draw my parabola, and there's our parabola. Another example says graph g of x, the translation of f of x equaling x, translated 1 unit and right 2 units. We'll make a table of values. So again, this one is saying g of x equaling, they're saying 2 to the right. It means this is a minus 2 here, and then it's up 1. So negative 3 minus 2 is negative 5. Negative 5 plus 1 is negative 4. Negative 2 minus 2 is negative 4, plus 1 is negative 3. Then negative 1 minus 2 is negative 3, plus 1 is negative 2. And these will just keep going up by 1s. And now I can plot those. Negative 3, negative 4. Negative 2, negative 3. Negative 1, negative 2. 0, negative 1. 1, 0. 2, 1. And there's my line. Next, use the graph of the function to write its equation. So the blue is the parent function. So f of x equaling, since it comes to a corner, this is the absolute value of x. Now g of x is related, but we just moved the vertex. So now inside the absolute value, the vertex moved 1 to the right. So that means I'm going to have a minus 1 in here, and then it moved up 1, 2. That's a plus 2. So it moved up 2. So our function would be g of x equaling absolute value of x minus 1 plus 2. Another example, the graph shows the translation of the parent function. What is the equation for the parent function the function? So the parent function is f of x equaling x squared. I know it's an x squared because I have a parabola shaped, and the parent function of a parabola is x squared. Now for g of x, or the new function, I know I'm going to have a x plus or minus in here, plus a number, and then it moved down because the parent function vertex is here. It's now down here, so it went down 1, 2, 3, 4. That means I have a minus 4 out here, and it went to the left 1, 2, 3, so that's a plus 3. And why is it a plus 3? Because again, when it's the parent function, x is equal to 0. So if I make this y minus plus 3 equaling 0, to make this find out where it moved, if I subtract 3 on both sides, I now have x equaling a negative 3, which is where I have my x coordinate. So that function would be g of x equaling x plus 3 squared minus 4. Next part is looking at dilations and reflections. Dilation means a stretch or a compression, and then there's also vertical or a horizontal movement with that. A dilation is a transformation that stretches or compresses the graph of a function. When we multiply a function by a constant, it dilates the graph with respect to the y-axis. Multiplying the independent variable by a constant dilates the graph with respect to the x-axis. So these last two statements is referring to where is the constant located. If the constant is located outside, or actually, if it's located inside parentheses or brackets, then it's reflected over the y-axis. If it's outside parentheses, brackets, or no parentheses, then it's reflected across the x-axis. And that's what this slide is referring to. So here, it's on the outside, so it's affecting the y. So if it's affecting the y, and a is the coefficient in front of your x is the absolute value is greater than 1, it's going to be a stretch vertically. If it's between 1 and 0, it's a compressed vertically. If the a is on the inside of parentheses or brackets, the absolute value is greater than 1, then it'd be compressed horizontally. Now, just to be clear, stretched vertically and compressed horizontally, the graphs are going to look identical. So they mean really pretty much the same thing. The only difference is when you write the equation, they would be slightly different. And then compressed vertically and stretched horizontally the graphs would look identical. The equations would be slightly different because of the location of our A. When we look at reflection is also a transformation where a figure, line, or curve is flipped in the line of reflection. Often the reflection is in the X or the Y axis. So you'll know that you have a reflection because you have a negative involved. When a parent function f of x is multiplied by -1, so instead of just f of x equaling x plus 4, if you have a negative in front of the function, it is reflection of the graph in the x-axis. So it's reflected across the x. It's affecting the y. So this is outside parentheses, brackets, or no parentheses. When only the variable is multiplied by -1, the result is f of negative x is a reflection across the y-axis. So inside parentheses, brackets. And that's what this table is referring to. Outside reflection across the x-axis that affects the y. Here, it's across the y-axis, affects the x. So our first example, in example 3, graph g of x, the transformation of f of x equaling x squared, compressed horizontally by a factor of 2.5 and reflected in the y-axis. So if I were to write the equation will help us create the table. So if it's compressed horizontally, that means I'm going to have it inside the parentheses. So if I have g of x equaling inside the parentheses, I'm going to have 2.5 x, and then I'm going to square this. I can have the negative, if it's reflected in the y-axis, it's reflected across the y. My x is going to, it's just going from a positive x to a negative x, but my y is going to stay the same. So I'm going to have a negative 2.5 inside the parentheses. It's not going up or down. So now let's choose some numbers. I'm just going to choose a negative 1, a 0, and a 1. You could choose other numbers, but I like to keep numbers very basic. So if I put a negative 1 in for x, 2.5 times negative 1 is 2.5, negative 2.5. Actually, no, a positive 2.5. And 2.5 squared gives us 6.25. And if I put a 1 in, just remember there's a negative there, negative 2.5 times 1 gives us a negative 2.5. Square that and we get 6.25. And if I put a 0 in there, 0 times negative 2.5 is 0, 0 squared is 0. If I plot these on my coordinate plane, I have negative 1 and 6.25. That would be roughly here. And then I have on the positive side, and then 0, 0. So you can see that I have a very narrow quadratic because I'm compressing it. I'm squeezing it horizontally. So I'm squeezing it towards the right, have my left side and the right side go towards each other. Next graph, g of x, the transformation of f of x equaling the absolute value of x compressed horizontally. So that one's going to look the same, but this one is reflected in the x-axis. So it's reflected across the x. So the negative is on the outside of our absolute value. So I'm going to have g of x equaling a negative, and then the absolute value, this would be a 2x. Now the 2 could be on the outside. No, the 2 has to be on the inside because this is a horizontal compression, so the 2 is on the inside. Now if I choose the same numbers, I'm going to do -1, 0, and 1 here. If I put a -1 in for x, -1 times 2 is -2. Absolute value of -2 is 2 times a -1 gives me a -2. 2 times 0 is 0. Absolute value of 0 is 0 times -1 is 0. 2 times 1 is 1, or 2 times 1 is 2. Absolute value of 2 is 2 times -1 is -2. So now if I plot these, I have a point at 0, 0. That's my vertex. -1, -2, and 1, -2. This one opens downward. The parent function would open this direction. Okay, so we are looking at this bottom part. Next, describe the dilation and reflection in a g of x equaling -2.5x as it relates to the parent function. So here we're not graphing, we're not writing the equation, we just have to describe the dilation. So g of x is the dilation, or is the transformed function. So we know 2/5, so we would say it's not in a parentheses, so this is a vertical compression. It's compression because it's less than 1, but greater than 0. There's a reflection, and we'll do compression by 2/5, and it's reflected over. It's now affecting the y coordinates, so it's reflected over the x-axis. Next, describe the dilation and reflection in g of x equaling -2.75x squared as it relates to the parent function. And then we're going to graph it on our graphing calculator. So there's no parentheses. This is a horizontal change. And the absolute value of -2.75 is 2.75, which is greater than x, or greater than 1. So this is a vertical stretch. I think I said horizontal, but this is vertical stretch by 2.75, and then it's reflected over the x-axis. Again, because it's affecting your y. So now if we grab our calculator, and we're going to graph this one. So I'll clear what I have in here, go to y equals, clear this. So if I do the parent function is x squared, and the y, and the translated one is -2.75 x, and then I square it. Then if I graph, here's the parent function, here's the translated function. So you can see that it reflected over the x-axis. It's now stretched, so it's longer or narrower than it would be with the parent function. Next part. The general form of a function is g of x equaling a times f of x minus h plus k, where f of x is the parent function. Each constant in the equation affects the parent graph. So again, as a review, the value of a, the absolute value of a stretches or compresses, which we use the word dilates, the parent function. When the value of a is negative, it's reflected across the x-axis. That means when a is not inside the parentheses. The value of a shifts or translates the parent function left or right. The value of k shifts or translates the parent function up or down. all depending on the sign given. So in g of x equaling a times f of x minus h plus k, each constant affects the graph of f of x equaling x squared. Now, if this was x squared, I would have to put a square on the outside to show that this is a parent function of this function here. Before we get to that example, just another quick review of dilations and reflections. So if a is bigger than 1, then you're going to have it's going to be stretched vertically. And if a is between 0 and 1, it's going to be compressed vertically. So it's going to be a little bit wider. And on the right side with reflection, if a is positive, it opens upward. If a is negative, it opens downward. And then the translations, horizontal, right and left. If h is positive, it goes to the right. If it's negative, it goes to the left. If k is positive, it goes up. If k is negative, it goes down. Now to our first example of example 5. So let's graph g of x. The transformation of f of x equals the absolute value of x compressed vertically by a factor of 2/3, reflected in the x-axis and translated 3 units left and 1 unit up. So I like to write the equation first because I think that makes it easier when you put the numbers in your table. So g of x equals, since this is reflected in the x-axis, it's affecting our y's. So that means I have a negative on the outside. Since this is compressed vertically, this is a vertical translation, I have the number 2/3 on the outside. And then I have the absolute value of x. It says 3 units left, so that means I have a +3 inside here, and then 1 unit up, so +1. So you could put this in your calculator the way it's written there and then use the table feature. Here I'm just going to come up with some numbers to plug in there. So the vertex is going to be at -3 and a +1. So I'm going to put -3 and a +1 right here. So that'll be our vertex. So now if I choose let's just choose a negative. Let's actually do it on our calculator to come up with the table of values. I think that would be the quickest way for that. So if I go back to my y equals, I'm going to clear everything I have. And then I'm going to type in the equation. So I have negative, I'll do a parentheses, so -2 divided by 3. And then I'm going to multiply that by the absolute value. So I go to numbers. Number 1 is absolute value of x plus 3, end parentheses, and then I'm going to add 1 to that. So if I graph it, this is what my function would look like. If I go to second graph, I'll see a table of values. And if I go up here, you can see right here, -3, 1 is my vertex because each of these numbers on each side repeat. So I want to just deal with whole numbers. So if I have -3 and 1. Let's go up one more. So I can do -6 and -1. And then I can also do 0 and -1. Now if I were to graph that one, so I can plot those. So I have -6, -1. I have -3, +1. And then I have 0, -1. And then I can draw my graph here. There's the transform function that we would have from there. The parent function again would be right here. So this point went 3 to the left and then up 1. And everything was reflected over, so you flipped it and it would open downward. Next one. Graph g of x, the transformation of f of x equaling x squared, translated down 5 units, right 3 units, and set vertically by a factor of 2. Since this is a vertical, this is, the 2 would be on the outside. There is no reflection, so we would have g of x equaling 2. We have x squared, actually parentheses, I would have x 3 units to the right, so that's a minus 3 squared, and then plus, or minus 5. Again, my vertex would be 3, negative 5. So if I do 3, negative 5 here, now let's just choose some numbers. If I put a 2 in for x, 2 minus 3 is negative 1. Negative 1 squared is negative 1 squared is 1. 1 times 2 is 2. 2 minus 5 is negative 3. If I put a 1 in for x, 1 minus 2 is negative 2. Negative 2 squared is 4. 4 times 2 is 8. 8 minus 5 is 3. I put a 4 in for x. 4 minus 3 is 1. 1 squared is 1 times 2 is 2. 2 minus 5 is negative 3. I put a 5 in for x. 5 minus 3 is 2. 2 squared is 4 times 2 is 8. 8 minus 5 is 3. And if I did another one, if I put 6, 6 minus 3 is 3. 3 squared is 9. 9 times 2 is 18. 18 minus 5 would give us 13. So we have enough points to plot. So I have negative, we can do 1, 3. We have 2, negative 3. We have 3, negative 5. We have 4, negative 3. And we have 5, positive 3. This is just a quadratic, so this is a parabola shape. So it comes down with a curve, then comes back up. And that would be the graph for this function. Example 6. Now apply it with a word problem. Suppose the path of a dolphin during a jump modeled by g of x equaling negative 0.125 times x minus 12 squared plus 18, where x is the horizontal distance traveled by the dolphin and g of x is the height above the surface of the water. Describe how g of x is related to its parent function and interpret the function in the context of the situation. So for this one, we want to identify our A, our H, and our K. Our A is here, so our A would be a negative 0.125. Our H is right here, which will give us 12, and our K is a positive 18. So to describe it, there are some translations. Since our A, or our H is 12, and 12 is greater than 0, this is translated 12 units to the right. So let's move 12 to the right. Our K is a positive 18, which means we move it up 18. There is a dilation because we do have our A, and our A is a negative 0.125. The absolute value of negative 0.125 is 0.125, which is greater than 0 but less than 1. This is a compression. This is vertical because it's on the outside of the parentheses. So it's vertical compression. And since A is negative, it's a reflection across the x-axis. And it's a reflection across the x-axis because it's on the outside of the parentheses, therefore affecting our y value. Now to explain the meaning of our transformation, because A is negative, the path of the dolphin is modeled by a parabola that opens downward. So that means the dolphin is going down. So it goes up and then it comes back down in here. This means that the vertex of the parabola HK represents the maximum height of the dolphin. So the maximum height the dolphin got was 18 feet at 12 feet from the starting point of the jump. Next, guide wires are used to add stability to structures such as towers, ship masts, and wind turbines. Suppose that two guide wires of a cell phone tower can be modeled by the function g of x equaling negative 1.43 times the absolute value of x plus 45, where x is the distance from the tower in meters, and g of x is the height in meters. Describe how g of x is related to its parent function. So the first thing, our a is a negative 1.43, our h is 0, and our k is a positive 45. So this one is, since it's on the outside of our absolute value, this is a vertical. And the absolute value of 1.43 is 1.43, which is greater than 1. So this is a vertical stretch by 1.43. It is reflected over the x-axis because the negative is affecting our y, and it's shifted 45 units up. Next, write an equation for the function listed here. This is an absolute value function, so the parent function would be the absolute value of x. We want to do the transform function, so g of x equaling, I have the absolute value here. The vertex has moved. The vertex moved 1, 2, 3, 3 steps to the left. That means I have x plus 3. And then it went down 1, 2, 3, 4. That means a minus 4. Now I need to find what a is. So to find out what a is, there is no reflection. So this was just moved. So to find our a, we need to choose an x and y on our graph to plug in. So if I choose this point right here, that point would be when x is 0, y is negative 3. I have a here, x is 0, y is negative 3, and then I can solve for a. So here, this would be 3, absolute value of 3 is 3 times a, so I have 3a minus 4 equals negative 3. If I add 4 to both sides, I now have 1 equaling 3a. To get a by itself, I divide by 3, and I would have a equaling 1/3. Now I can take that and I can plug that back into my equation, and I would have g of x equaling 1/3 times the absolute value of x plus 3 minus 4. And that would be our function. Next, use the graph to write the equation for g of x. So g of x is the purple one here. So again, there is no reflection involved with this one. So I'm going to start with g of x equaling, I'm going to have an a on the outside. It did move, the vertex moved to the right, so that means this is a minus. Minus 1, 2, 3, 3 to the right, and then it went up 2, so that's a plus 2 as our k. Now I need to choose a point, and I'm going to choose this point right here, and that would be 1, 2, 3, 4 for your x. And my y is 1, 2, 3, 4, 5, 6, 7. Then I can solve for a. 4 minus 3 is 1. 1 times absolute value of 1 is 1 times a is a. Plus 2 equals 7. Subtract 2 on both sides. And a would equal 5. So now I can write my equation, g of x equaling 5 times the absolute value of x minus 3 plus 2. And our last example, write the graph of, use the graph to write the equation for g of x. They're telling us the point to use for this one. So g of x equaling, need to find a when the vertex, this is actually a parabola, so this would be parentheses x. It went to the right one, so that would be minus 1 squared. It went down 1, so that's minus 1. We're going to use 2, 5 for x and y. So I have a times 2 minus 1 squared minus 1 equaling negative 5. 2 minus 1 is 1. 1 squared is 1 times a is a minus 1 equals negative 5. Get a by itself, I add 1 to both sides, and I'm left with a equaling a negative 4. So my equation would be g of x equaling negative 4 times parentheses x minus 1 squared minus 1. And that is our lesson on transformations of functions.